Advanced Math, Set 101, 0 determinants, 3 by 3 determinants, determinant solutions of 3 by 3 systems, and independent equations. Okay, so the first thing we'll talk about are 0 determinants. And here you have two matrices of numbers. A determinant is associated only with a square matrix. So when we look at these two matrices, the first one is a 2 by 2 and the second one is a 2 by 3. If it is not square, there's no determinant. So the first one is a square matrix, so it does have a determinant. The second one is not square, so it will not have a determinant. Okay, a determinant is a number, and so even if you have something that looks like this, it's also called a determinant because that's the label, it's representing a number. The value of this particular matrix is 4 times 1 minus 2 times 2, which is 4 minus 4, which is 0. Okay, with Cramer's rule, 0 determinants in the denominator tell us that the equations don't have a single common solution. So for example, here's a matrix, or here's a set of equations that we want to solve. And if we multiply the bottom by 2, we can see that they are going to match up. So we end up getting 4x plus 2y equals 28 on the bottom. And since those match, we can tell, we can subtract everything. We get 0 equals negative 20. And if we use Cramer's rule with that, putting the solution for x, 8, 14, and then 2, 1 for y, and then 4, 2, 2, 1 for x, we're going to get 8 times 1 minus 2 times 14 over 4 times 1 minus 2 times 2. 8 times 1 is 8, 2 times 14 is 28, 4 times 1 and 2 times 2 are both 4. 8 minus 28 is going to give us negative 20, and 4 minus 4 is 0. We'll have a 0 in the bottom. If we do the same thing for y, you're going to have 4 times 14 minus 8 times 2 all over 0. So that's 56 minus 16 over 0, or 40 over 0. And we can just tell there's not going to be a single solution in this particular case. Okay, now we'll talk about 3 by 3 determinants. So what if you do have a 3 by 3 matrix, how are you going to figure out what the determinant is? So if I have a general set of equations that I need to solve for, like this, I've got x, y, and z, and I have coefficients in front. I have coefficients a, b, and c in front of all of the x, y's, and z's, and that's equal a constant. If I was going to solve for this using elimination, it would be pretty tricky, but it would look something like this. If we use elimination to solve just for x, the answer is going to look like this, which is pretty messy. There is a pattern there, but it's kind of hard to see what the pattern is. It's actually easier if we use Cramer's rule, because we can kind of line it up this way. So the determinant, this is for solving for x. We're going to put the constant where x is, and then leaves, and this is talking about the numerator. We'll put the constant where x is, and then the b's and the c's go in the normal, where they normally would. And then on the denominator, you just have all of the coefficients of your system. So in this lesson, we're going to use a particular method to find the determinant. You'll also have other methods later, but this particular method only works for 3 by 3 matrices that we're going to learn today. So here's how you do it. If you have a 3 by 3 matrix and you're trying to find the determinant, what you're going to do is you're going to take the numbers that are in the matrix and you're just going to write them again. And then you're going to repeat the first and second columns. So we're just repeating 3, 1, 2 and -2 for -3. Actually, I'm just going to highlight them. So we're just going to repeat those and do those there. So now what we do is we go along the diagonals. So we're going to go upwards first, and so we'll say 2 times 4 times 1 is 8. And then we'll do the next diagonal, -3 times 10 times 3 is -90. And 5 times -1 times -2 gives us 10. Now we're going to go diagonal downwards. 3 times 4 times 5 is 60. -2 times 10 times 2 is -40. And 1 times -1 times -3 is 3. From here, we're going to add those up. So we, on the going downward, the green ones, we get 23, and going upwards, the red ones, we get -72. Now, this part is where you have to make sure that you're doing it correctly. You take the green and you subtract the red. So we're going to say 23 minus -72. So 23 minus -72 gives us a determinant of 95. Okay, so now how do you find the solution if you have 3 by 3 system? So you use Cramer's rule to solve for x, y, and z. So this is going to take a while to get the solution, but we'll go through it. So using Cramer's rule, we'll start with x. And actually, before we even start with x, we're going to figure out the denominator. So remember, the denominator in Cramer's rule are the coefficient of all of your system. So you have 2, 1, 3, and then 1, 1, -1, and then 2, -1, and 2. And then we'll just line it up the way that we just spoke about. So you have your determinant, and then add those first 2 columns again at the end. Then we will multiply going up. 3 times 1 times 2, -1 times -1 times 2, and 2 times 1 times 1. And then we'll go down, or actually, okay, add them. And so 6 plus 2 plus 2 is 10. Now we'll go down. 2 times 2 times 1 is 4. 1 times -1 times 3 is -3. And 2 times 1 times -1 is -2. Add those together, and we get -1. And we take -1 minus 10 to get -11. So our determinant on the bottom is -11. Now we're going to solve for x. So here's our system again. And in place of x, we're going to put the constants, the 7, -2, 16. Now we're going to go back to the constant, or the coefficients in front of the y's, and we'll put 1, 1, -1, and then in front of the z's, we have our 2, -1, and 2. And then we repeat our first 2 rows. Oh wait, so that's what we'll be solving for x, the determinant of that over -11, because that's what we found to be our determinant of our denominator on the previous page. So we write our determinant and the 2 additional first 2 columns, and then we will multiply. 16 times 1 times 2, -1 times -1 times 7, 2 times -2 times 1, 32, 7, and -4. So that equals 35. Okay, 7 times 1 times 2, 1 times -1 times 16, and 2 times -2 times -1. We get 4. So that, when we add it together, 14 minus 16 plus 4 gives us 2. 2 minus 35 is going to give me -33. So this is our value of our numerator. We have -33 over -11 because negative 33 is this value here for this determinant, negative 33 over 11, and that is equal to 3. So we know our x value is equal to 3. Now we need to solve for our y value. So with our y value, we're going to take the 2, 1, and 3 and put it there. Then we're going to take our constant, or our constant, which is the solution, 7, negative 2, and 16, put it in place of y, and then 2, negative 1, 2 for z. That's the determinant over negative 11 is going to give us our solution for y. So 2, 1, 3, 7, negative 2, 16, 2, negative 1, 2. Then repeat those first two columns. We'll multiply upward diagonally. 3, negative 2, and 2 gives us negative 12. 16, negative 1, and 2, negative 32. 2, 1, and 7 gives us 14. Multiplying down, or actually let's add those together. We get negative 30. So 2 times negative 2 times 2 gives me negative 8. 7 times negative 1 times 3 gives me negative 21. 2 times 1 times 16 is 32. Add those together, gives me 3. So 3 minus negative 30 gives me 33. Put that over negative 11, which gives me a y value of negative 3. Now we need to solve for z. So we'll put 2, 1, 3, 1, 1, negative 1, and then 7, negative 2, 16 goes in place of the z's. All of that over negative 11. So we'll put our determinant and then repeat the first two columns and multiply upwards. So there's the top. When we add that together, we're going to get 41. And then on the bottom, add those together, we get 19. So 19 minus 41. 19 minus 41 is negative 22. And so we get negative 22 over negative 11, so our z value is 2. So when we write our solution is 3, negative 3, 2, because 3 was x, negative 3 was y, and z was 2. Okay, so let's do another example. In this case, we just have to solve for z. We're not solving for everything, we're just solving for z. Here you have to be careful because they're not all lined up perfectly. Notice that the second one doesn't have an x and the third one doesn't have a z. So the first thing we'll do is we'll write our determinant matrix. So we have 3, 0, 1, 2, 2, 2, and 1, 3, 0. Just to be absolutely clear, 3, then there's no x here, and then there's 1 here. So 3, 0, 1 comes from there. And then our y's, we've got 2, 2, and 2. And then for z, we have 1, 3, whoops, 1 didn't show up, 1, 3, and then there's no z on the bottom. So that's 0. So that's where those came from. Okay, now we're solving for z. So let me clear those out. So we're solving for z on the top. So the x and the y are going to be the same. And then the z is going, instead of the z, we're actually going to put our constants 9, 14, and 3. So we'll put everything else the same. And then we need to find the determinants of these two 3 by 3 matrices. So we'll do the top first. We put the determinant and then repeat the first two columns, and then we're going to multiply diagonally upwards. So we get 18, then we're going to get 84, and then the zeros are nice because you just have to put 0. So 18 plus 84 plus 0. Then 3 times 2 times 3, 2 times 14 times 1, 9 times 0 times 2. Add those together. So 18 plus 28 is 46. 18 plus 84 is 102. 46 minus 102 is negative 56. So we know that negative 56 goes on top. Now we'll do the bottom. Again, we're doing the denominator and then repeating those first two columns, multiply upwards. So we get 2, 18, and 0. Multiply downwards, we get 0, 6, and 0. When we add, we get 6 and 20. 6 minus 20 is negative 14. So we have negative 56 over negative 14, which equals a positive 4. So in this case, z is equal to 4. Okay, independent equations. If you have an n by n system, so if you have a square system, all n systems must be independent in order to have a unique solution. So if you have a 2 by 2, both systems have to be independent. If you have a 3 by 3, all three have to be independent, and so on. So let's do an example. This would be a case of a 2 by 2 that is not independent, and let's talk about why. If you take that first equation and multiply every value by 2, 4x times 2 is going to be 8x, 3y times 2 is going to be 6y. So you have matching x's and y's, which indicates, and then also your constant or your what it equals are not going to match. That indicates that you have parallel lines. And when you have parallel lines, there's no solution, and we know that it's not independent because there's not a unique solution. Here's another example. If we have this one, if we multiply everything by 2, 4x times 2, 3y times 2, and 1 times 2, everything's going to match up. And if that's the case, you're going to have overlapping lines. Every point on those two lines is a solution, so it's not a unique solution. So these are not independent. So if we do the determinant of both of these systems, they both have 4, 8, and 3, 6. So 4 times 6 minus 3 times 8, you're going to get 24 minus 24, which is 0. So the determinants are going to be equal to 0. So an n by system of linear equations is an independent system if there's two conditions here. You can tell it's independent if no row in the coefficient matrix is a product of the constant and the members of another row. So in other words, if you multiply and then multiply something by one of the rows, you're not going to match up with another row. And secondly, if no row of the coefficient matrix can be formed by adding multiples of 2 or more rows. So we'll go into more detail here. So here's an example of a matrix. This is not independent because if we take that first row and we multiply everything by 3, we end up getting 3x plus 9y plus 6z equals 3, which exactly matches the row underneath it. So we know that it's not independent. Okay, here's a second one. If we're looking at this one, if you look at it, you can see if I multiply any of the bottom ones by 2, it's not going to match. So that looks good, but then we have to go to our second condition here. It says no row of the coefficient matrix can be formed by adding multiples of 2 or more rows. So if I add these two together, 2x minus x, I get x, y plus 3y equals 4y, negative z plus 2z equals z, and 4 plus 8, well, the constant doesn't matter. So if I add those together, it's not independent. Okay, so why does this matter? The determinants will equal 0 in this case. So if you have this case where you have multiples of each other, or they're a couple of the equations add up to get the other one, your determinant will automatically be 0. Okay, so last example. We've got a couple of systems. So these are the systems we were just talking about. We're going to show that the determinants are going to equal 0. So we're going to write out the matrices here, and we will find the upward diagonal. So 9 times 2, 4 times 6, 2 times 3 times 3. When we add those together, we end up getting 12. Okay, if we go downwards, 9 times 2, 3 times 6, 2 times 3 times -4, add those together, we get 12. And you can see 12 minus 12 is going to give us 0. Okay, on the blue one, same thing, we'll write out the determinant and then the first two rows, go upwards, -3, 16, -1. That gives us -3 plus 16 minus 1 is 12. When we multiply downwards, we get 6, 2, and 4. When we add those together, we get 12. 12 minus 12 is 0. So the determinants of those two systems are 0.